swing back to Euler and Hamiltonian. Right? Remember, easiest way to remember which is which. Euler starts with an E, and he cares about edges on the graph being traversed exactly once. And then Hamiltonian would be our other situation with the vertices, right? So either traverse all the vertices or traverse all of the edges. You come up with any questions since we talked about this last week? Nothing. Everybody's good for the moment. Anything questions about the cut edges or vertices? Am I still talking on mute? Everyone's still coming back from the break. All right, any questions about graphs at all? It should be everything you need to talk about for the graph section. People can't hear me, right? Make sure my microphone didn't die on me. It's awfully quiet. All right, good, good. I thought so, but always good to check. All right, hashing. Hashing is a one-way cryptographic algorithm that takes bunch of just takes data and chops and mixes it together. All right, so let's get the Wikipedia up here. Take a quick look at a couple of MD5 is not as commonly used anymore. At least it shouldn't be due to lack of security, but not necessarily going to be using the hash as a security feature. So MD5 can still be used for other purposes. There's part one down here. All right, so we're going to look at the very basic, simple ways of hash functions and breaking pieces down into smaller things. But MD5 is pretty fast. I mean, it should be linear in proportion to the data. I see the logic of it pretty much here. Just start chunking our data into small pieces and anding and oring it together right here. So here's down here the symbols. Let me get my Right down here at the bottom, we have what these notations are, right? Exclusive or, and or not. So it's going to take the values, take so many bits of the binary. But yeah, hashing is fairly quick. But if you're hashing a megabyte versus hashing 5 megabytes, it depends on how much data you're going to be hashing together. And it doesn't really matter too much what hash algorithm you're talking about. They're all going to have similar complexities. But we'll break the data into blocks and we'll smash the bits together. And this ends up being a one-way transformation of the data. Okay. Other Shaw. All right. Secure hash algorithms. This one's a little more used with cryptography in mind. A more modern way of doing things, or it's the same idea, right? Message digest. There's several versions of message digest. It's been around for a long time. Then Shaw came along, and we made things a little bit bigger and stronger. And they keep on getting newer versions. I think Shaw 2 right now is the most commonly used one. I think Shaw 3 has been 2012. Not a lot. Things are just using SHA 3 just yet, but as newer and newer cryptography come out, like how many bits? Like, so another area of cryptography, right? HTTPS, TLS, whatever. Those are two-way functions where you can go ahead and encrypt plain text into a ciphertext, and then on the receiving side, if you have the appropriate key, you can take the ciphertext and turn it back to plain text. Right, with a hash, basic idea is take the text of data and do a one-way transformation of that data into something else. All right, so D5 and SHA algorithms, algorithms are hash functions. Right, just like hash browns, right? Hash browns were a potato, but they've been chopped up, mixed together, cooked together, and so trying to figure out what the potato looked like before it got turned into hash browns is going to be basically impossible. You might have an idea of, okay, this was a potato before it got hashed, but afterwards, you're not going to be able to get back to the original function. All right, so simplest hash function that we're going to be talking about is division. All right, so our division function, I might as well put in front of here, takes the key and the module value and sends it back. All right, so say the modulo, well, let's just do table. And that's probably enough. All right, so for keys 10, 20, 30. Yeah, let's get a few more values here. 34, 14. So mod 10, right? Take the number, divide by 10, whatever the remainder is. That is our hash value. All right, so 10 by 10 is no remainder. So you can see that these three values, these hash values, 0, there's no way to know if I give you a 0, was the key originally 10 or was it 20 or was it 30? It's no way to know. Same thing with 4. The number of possible keys that result in that particular hash value it's going to be very difficult to reverse that. All right, 5000 4 and 4. Now I check my math, make sure my math is working here for these ones, just to make sure, but that's the basic idea for that hash function. Let's go look at some practical use of this. Let's see what we're looking for. On the files section, files. Down in hashing. There's a more hashing zip file. Nope, not this one. I want salty hash. Yeah, this is written in. Where the heck is my extract button? There you are. This is a .NET program or a window. Let's get the right window. And go dig down into the debug folder. There will be executable, but you can also look at the code if you want. We'll look at that in a second. All right. The executable is not signed, so you'll have to hit the yes, we want to run it anyways. Trust the code. If you don't trust the code, you can just take the code and compile it. Assuming it still runs. There we are. Just decided to go underneath the screen. All right, so one of the most common places that hashing will typically use will be with securing passwords. Passwords are sensitive data. Typically, you're advised not to share your password with other people because that means your account could be compromised by anyone who has your password. And it's even better if the system that you're storing your password in also doesn't have the ability to know your password. It's been a long time, but I know I've gone through some websites. I say it's twice now. Forget passwords. Sure, no problem. And it emails your password to you. Well, there goes that password security because it's now gone through an email system, which is not secure. And plus, the website that I was asking for my password for actually knew what the password is. It means trust in that merchant's website should not be given because even the website shouldn't know the password. And the way we're going to make that work is with hashing. And so the basic pattern is you go create an account, all right, give a username, provide a password, and then you go ahead and register your account. Now you have your account. And then when you want to log in the future, come along and you type your password, you hit login, and if your password matches what's in the database, then you're good to go. And if it's not matching, then we don't let you log in. What we're doing here, when we create our account, right, the username is just plain text, store that in the database. So when we go log in and type the correct password, right, we get a successful login. But the password that we store in the database is not what was typed in the password box. What we do is we put this through a hash function. This is going through MD5, which we'll see is not secure in a second here. And we hash it. So we take Cuevas, run it through the MD5 hash function, and then we take the hash value that came out of that function and we persist that to the database. When I go to log in, we've got the username, we take that, pull that from our database, pull the hash password, hash the password that was just provided, and then compare the two values together. There's even just a single bit difference, right? Uppercase and lowercase. characters in the alphabet, there's only 1 bit difference there, and you can see that the corresponding hash, even though there's just a single bit difference, significantly alters the value that comes out of that. All right, go back to little c, go to a big S, we can flip the other side of things. All right, so nothing at all. Let's see, where's the first one here? All right, so let's do a browser, type that into Google, and we'll see that we get a hit for that. You can see that it is popping up Cuevas here, which is our password. So what happened here is a reverse dictionary attack. So they didn't actually, Google didn't take this string of hexadecimal characters and then, reverse the math to figure out that Cuevas was what was used to generate the password. Let's see. All right, let's get a more secure password. Password. There we go. Register that one. Let's try that one. See if we can get this one to show up. All right, MD reverse. And it was password. Right. Password tends to be not a good password. Just in case you're not noticing there, password is a very bad password. So reverse lookup is basically do a dictionary attack and take all commonly used words that are often used for passwords and then run them through MD5 and then create a dictionary of all of the hash values. And we do a reverse lookup so we can get back the original value by looking up from a hash table, probably, that value, and then map that to our password. So the next line of defense, aside from the website enforcing password rules, it has to have an uppercase character and a lowercase character, right? Like I had over here, capital C, which might be enough. Yeah, it looks like capital C is not confusing at all. Let's go for the capital S. Looks like a capital S took care of things for us there, right? So capitalizing the first letter, not a good pattern. Capitalizing a random position in the word, that's going to work out better. So that's why there are password rules there. Password rules help fight against the reverse lookup because the number of possible combinations of a 6 to 12 character password, when we have alphanumeric, where alpha, upper, and lowercase are different, numeric, underscore, special characters, right? Combinations grow quickly here. Let's get a calculator. Right, you got 52 possible letters, plus 10 digits, plus say about 15 valid special characters that they're happy for you to use. Certain special characters might not be allowed. I've seen that before. It's kind of weird, right? They're trying to prevent attacks against the database, SQL injection attacks, because like dash dash would be a common character used in SQL injection, right? Star also possibly in use there, and the equal sign. This would be a good off-topic thing to read about. Go read about SQL injection attacks. I've only actually seen code one place where that it was susceptible to that. But anyways, right, 77. Let's try that again. 77, right? Even only at 6 characters, right? Number of passwords gets in the billions. Got 77 to a reasonably length password, 10, right? Number of possible passwords just becomes too much to try to preemptively attack for a reverse lookup. Now, all right, password. To get some even better security, what we'll do when creating an account, right? User does the same thing as they did before. They provide username, password, and what we'll do is we'll create a random value associated with that particular user, and we'll use that to hash the password. So it's the same process as before, right? Login successful. Take the password, take the username, look up the username, look up what their hash password is, look up what their salt is, and then go ahead and combine the password provided by the user and the salt, put those two together, then run them through our hash function and then produce a new hash value. Right? So if either of these two comes up with a result, I would be extremely shocked because that means having to do a dictionary attack. I guess that we're getting an ad over here. 5-star rating. Right? So that means doing a dictionary attack in composition with a salt, which is a bunch of random case sensitive values again, because we're pushing that through a hash code. So it becomes even difficult to compromise the account, even if the database itself gets compromised. I like to pick on the PlayStation Network because it was 6, 8 years ago. Let's say they had twice in the same year, PlayStation Network had user credentials compromised because they stored the user accounts in basically a flat file on a machine out there somewhere. So what exactly the salt? Salt's just a random value. So it's kind of like take a salt shaker and just dump some salt out on to a plate. Like you get basically a chaotic random value for the arrangement of those salt crystals. I'm presuming that's where they got the term salt for it, but it just represents some random value that we'll create to associate with the user. And so if this database were compromised, say someone, I forgot to change the default FTP password into our Windows server and the port was open. And they just, type in the admin1, whatever the default password is for the OS, and they gain access to the file system, and our database is just sitting in the file system, and this data gets corrupted, right? They would have to run the dictionary attack against all possible passwords that they have in their paste bin file that we saw earlier there, along with the salt, however it is combined. And there's different ways we can combine it. Look at the code that I have. Just very simply, we just concatenate the two strings together, but we can get fancy if we wanted. We could go ahead, compare the lengths here, grab a couple characters, and weave them together. Right, so we can get even extra security there, because then, assuming the the hacker only has the data and not the code that we're using to run through it, they even still might be unable to actually successfully impersonate any of the users with the reverse lookup credentials. All right. Find the code. Right, it's in C#. Right? This is not code that you need to worry about for this class. Just want to show it to you in case you are interested. All right, so we're going to create salt. Right, just creates a random array of bytes. Right, so however many bytes we told it to create, just create an array of bytes, and then populates that array of bytes via a .NET library, just generate a random value. Right, so it generates a random value. Right, the way that we create our password hash, right? Password comes along, salt comes along, smash those two strings together to a bigger string, and then we call an MD5. Go ahead and hash those two together. And it just builds up our byte array of data, computing hash using the library function, and then we just build our byte array into a base 16 representation, so it's easier to see it on the screen. All right, so there's, assuming the language you're using has libraries, there's really not a whole lot to do code-wise to set up this pattern. I was actually at a company that decade ago where they didn't have salty hash time. It's one of those things, once you built the system, and all of a sudden you have millions of users in the system, getting things to work forward, a little bit tricky, but let's see. Do we use getLine for the password, or is it a simple string? Well, however you get your string, you would get your string. And this is a Windows Forms application, so it's all C# in there, just pulling from properties of the Windows Forms. User interaction within Forms-based applications is a fair bit different than it is with console-based applications. So that's its own thing. I mean, at the end of the semester, if there's interest, I can show you some C# stuff, things like that, forms. Just one of the many languages out there that is available to you, possibly. Okay, so cryptography. All right, one-way cryptographic algorithm. That is a common scenario for which hashing would be used. It's when we don't need to get the original data back, but we can then basically recreate the data and use it for logging in. I think there's probably other uses for this. Trying to think mentions anything here. I can't think of anything else at the moment. But that's as far as we're going to get into cryptography in this class. That's another area. I'm trying to think of any courses. There are courses that are specifically for cryptography, tend to be a little bit math heavy and electives. So you may or may not take any cryptography courses, but if you don't take a course, it's something I recommend. You taking a look at. I'm not going to post a link for this, but there's symmetric. I'll post it in the chat in case you are interested in looking at things. Asymmetric. Okay. And these are very, very commonly used. All right. Right now we're using HTTPS, so that's using transport layer security, which is going to be symmetric. Then you typically exchange keys, and it's going to go to asymmetric. But yeah, so this is going to be very, very commonly used patterns. You don't need to know the math behind this. So I recommend reading up on it because it's definitely something you're going to very likely have to use out there in industry because people don't like it when their data gets compromised, and businesses are also of the same opinion. They don't like it when their data gets compromised. So they will try to protect the data as best they can. And security is one of those fun pain in the butt things. As long as there's enough of it, it'll help keep people out. But there are a lot of, I think this is the website. Yeah, so there's a lot of cyber warfare going on all the time out there. So there's interesting websites to go check out and show things. It's actually not showing a lot of activity at the moment. Usually I see a lot more activity going on. But right, be mindful of malware and phishing, right? Don't go to websites you don't trust. Don't install plugins you don't trust. Be very careful installing extensions, right? Extensions typically have access to everything on the page. Just be careful. All right, hash functions. Post the link. Yes, I did. All right, division, which talked about. It's going to be key modulo a value. It's square. Someone's right. I'm not a big fan of the name. But we'll take the key value, square it, and then pull out a middle section of that key. All right, so we'll do mid square 3, keeping 3 positions, and we'll resume zero filling left side. So let me show you some data, try to help explain what I'm talking about. Let's just do some numbers. Bust the calculator out again, help us do some of our math. Because I'm okay at 12. But 123 squared. That's gonna be a bit too much. All right, so the middle 3. We have a nice odd length. Getting the middle 3 is gonna be easy. Hopefully we can get something that is not odd in length here. I have to keep playing with different data points. But we've got 2 extra at the front, 2 extra at the end, 227 for our middle. Just my luck. Everybody's being nice and odd. All right. Let's go for 255 squared, see what we can get there. All right. 455. There we go, 6 characters. 455, 6 characters, right? So basically, pretend that there's a 0 at the front, and we'll keep those 3 middle values. Our key is 070. All right, so like any other hash function, the number of different keys that can make 144 or will be numerous. It's going to be basically difficult to impossible. Since these hash functions that we're talking about right now are pretty simple, it's not too difficult to point like, okay, 144, right? Well, try to come up with all the numbers. That's square, so it's 144 in the middle. That'll be a somewhat small set, so we can go ahead and try to do a tumbling attack where we just keep trying different passwords against a known username to see if anything sticks. And this is where the website needs to be like, you've had too many past attempts to log in today. Let's go ahead and pause for a day and you can try again tomorrow. Right, so the middle 3, right? So we'll take the length of the squared value minus the length of the middle we want to keep, divide that number in half, and then strip that number of digits from the ends of the square. All right, so in our first one, we had to strip 0 digits away. Second one, we had 5 minus 3 gave us 2. 2 divided 2 is 1. So we took off leading and ending digits. All right, so if we have a fractional, all right, so we'll start stripping from the right side and then go back and forth until we have stripped away the edges, leaving the middle. All right, starting on the right side means we strip away the 5. All right, so here we have, if I don't zero pad, we have 6. It leaves us with 3 characters to strip away. That by 2 gives us 1.5. So first one's the 5, second one's the 2 on the left, and the third one's the 2 on the right, and then we're left with 0, 7, 0. Yeah, if it's smaller than, right, so we got 9, 081, and 081 would be our middle 3. Because we left pad the value on the as a 0, and that doesn't change the integer, it's still just 81. We'll look at some more hash functions later. That's good enough for now. We'll talk next about a hash table. Yeah, we take away from the right and left. I would word it, we take away from the right and left since we're going from the right side first. Unless you're zero padding. If you're zero padding, it doesn't matter which side you go first, because then we'll round the number up after dividing by 2. And a hash table. What do you mean? What about values 1 through 3? All right, so there are fewer digits. Right, we zero padded on the left. So we zero padded over here to make it an odd length, and I zero padded over here to make an odd length. That's because I had middle 3. Right, so if I had a middle 4, and I want even lengths, because 8 less 4 in the middle means there's 2 on either side of it. Let's do that example while we're here. Since there are questions mean it's a good idea to do more examples. And well, we've got the data already. May as well use said data. This time we'll do middle 4. All right, so the middle 4 values, because we'll zero pad just to make an even number of data points to split off either side. All right, zero pad. Gives me the middle 4 values. All right, we had 9 here, so split that up to even it up so we have an even number on either side. All right, so here's the middle. We have 3 digits to the left, 3 digits to the right. We get a middle value. That one already had an even number digits, so we don't have to pad it. And this one we have to pad even more. That gives us a middle section of it. Yeah, the key is 2. It's the same as it would be with 9. Yeah, middle 3 would be 004. Yeah, we wouldn't have to pad it as much. All right. Any other questions at the moment on this particular page? Happy to answer. Okay, hash table. A data structure that will make use of hash algorithms to quickly add and look up data in the underlying structure. All right, so the pattern is we'll take a key, feed that key to a hash function, MD5 or something like that. Take the resulting hash value and then normalize that value into an index in the table. All right, so there's going to be, right, so the hash table will be an array. Might just be a flat array or an array of linked lists or an array of buckets, an array of some sort. Normalization is taking hash value and then applying modulo of that value based on the table size, thus giving us an index with which to use in the table. Yeah, we'll pad it all just so that it shows the right number of digits, right? If it gets stored as an actual integer variable in memory, right? All integers are inherently zero padded. We just don't bother showing them typically when outputting them to the screen or wherever they're stored. All right, so given a hash table, size 7, using its square, we'll do 2. What are the indices that we'll try to use for the following set data? All right. Chi square mid index, which is going to be the value mod 7. 10, 12, 16. What was it, 196? Correct my math if I'm wrong. All right, so our mid 2 should be along those lines. Right? We have an even mid, so we want to make our squares look even so it's easier to see which parts we're keeping. 16 is 256. Oh, that's terrible. My brain. 256. Oh yeah, I should have known that. That's a nice base 2 number. go, 25. What was I doing? 19 squared in my head? Anyways, take our hash value. All right, so right now our table, we have indices 0 through 6 as valid inside the bounds of the array. 25 is not a valid index. 10, right, none of these hash values are good indexes. So what we want to do is normalize via our modulo and transform those to an index in the table. We are going to have a problem with 16 because we already have someone sitting there at index 4, but that's the index we're going to try to use. That is what's known as a collision if we do get into that situation. And we can solve for that as well. And collisions are what's going to drive us away from our ideal O notation, which is going to be constant time. All right, adding values. Initially, the table will be empty. The way we indicate this is the load factor is 0. And load factor is just the number of occupied positions in the table divided by the table size. All right, so 0 divided by 7 gives us load factor 0. Load factor tells us probability that a new value being added to the table will result in a collision. And collisions will cause us to degrade performance. So we'll take normalized value and drop value at that index in the table if that cell is empty. If that cell isn't empty, then we'll run it through collision resolution. A good chunk of this section of the course is going to be by hashing hash tables, most specifically. So when you get around to studying for the hash table test, which is still a little ways off, hash table, the fifth test, hashing is where we're going to be most of the questions. All right, so let's insert our table. So we'll have our index and we'll have our data. All right, so our first value that we added in was the key 5, which ended up at index 4. So 5 finds its way into index 4. And another column to the left. 0, empty table. 1, we've inserted 5. Next key we're trying to add is 10. 10 is trying to get to index 3. Index 3 does not have anyone there, so go ahead and drop that in and be good to go. 12 comes along, ends up at index 2. No collision just yet. Everything's happy. But when 4 comes along, excuse me, when 16 comes along, that's also trying to go next 4. And we have a collision here. And that gives us a bit of a problem. Collision resolution. Right, there are several approaches to dealing with a collision. Where a collision is 2 different keys trying to occupy the same spot in the table. And the reason I say 2 different keys, the same key, of course, fight with itself. In fact, .NET library, if you create a dictionary type or a hash map or hash table type, trying to add the same key would be an exceptional or an invalid operation, and it will give you an exception saying no, nope, reject it because you're trying to use a value that is not actually a key. General idea of a key is that a key is going to be unique. Right? We don't have no master keys or skeleton keys. Well, that key just works for everything. Every key is going to be unique in the set of data so that we can use that to quickly identify the data we want and then load things up. So let me give a quick example of what you'll see this in the wild. Going back to our website where users were registering themselves and then doing whatever it is our website does. Right, so a website is typically going to have more than one user logged in at any given time. Tens of users, hundreds of users, thousands, millions. It just depends on how big of a website we have. Right, so here we're in Google docs.google.com. I imagine there's more than one person logged in at this point in time, right? We have 4 people at least on top also looking at it on their screen directly. And if this document was actually being shared for editing, Google needs to keep track of everyone is editing the document and doing operations on this particular document. So depending on our sharing permissions, the sharing might be only to a specific set of people, right? Lots of people can look at the content, only a certain number of people can edit the content. And every time there's an action, since, right, get our dev toolbar up here. Try to get our dev toolbar up here. And network, right? So every time, right, we do stuff in here, most of that is causing network traffic. All right, so it's all going to the same. I got a filter going on there. That's why. It's not showing me anything. Do things and show yourself. Well, let's try that again. Out the filter that I was using for some reason. Why? Yeah, whatever. It doesn't matter. How does 5 become a 4? Right? 5 got squared 25. And then we took 25 and divided by 7. And, right, 7 goes in there, 21 gives us a remainder of 4. Yeah, so I have mod 7. Cool. All right, so what the website would do is probably create a dictionary, everyone that's logged into the site. And every time a request goes back to the server and we're authenticating against that user has the permissions to do whatever we're trying to do, that's going to be done against the dictionary. Right? It may not be the username that's being used, it might be a session ID, whatever it is, but that data that's going to be used in the dictionary so we can look up user, the permissions, all that stuff that's associated with that user on our site. based on the session ID, username, or whatever. We want to do that very, very quickly amongst a potentially large set of people. And this is where hash tables are going to come in. Yeah, but sometimes we're going to have two different keys try to hit the same spot, and we'll have collision resolutions. So our simplest way of doing that is going to be linear probing. All right, so we will start at the collision site, and then walk down the road, the array, until we find an empty position. And we'll add the value there. All right, so look up. All right, so the primary two operations for a hash table will be add and look up. We'll take the key, feed it through the hash function, and try to find the data. In the same way that we added it, this time grabbing back the associated data with that key. All right, so all right, what was my key? It was 16, right? So 16 ended up over here. Our linear probe, so this one is out of position. So when we look up any value in our table, when we look up 5, we'll hash it, normalize it, and then index 4 is what we're looking at. So we'll go ahead and look at index 4. We see that there's a value here, and then we'll compare that value against the key that we're doing the lookup for. If it's a match, we'll go ahead and return the associated data. Same thing, 10 goes to 3, go to index 3, and then if the key matches, we're good to go. Key matches, we're good to go. Do our lookup for 16. 16, index 4, 16 is not found at index 4. So we'll have to do the linear probe just as we did when adding and start walking down the array until we find a matching key. All right, so doing the lookup, check key against cells till we find matching key or we find an empty cell. Note that both add and lookup will treat the array as circular. Just remember back when we were doing our array-based queue, that was a circular array. It means the index after the last index is the first index in the array. If the hash table has no more open spots, then we wouldn't be able to add data to it without rebuilding the table, resizing the table. All right, so yeah, full table would need to be resized. Yeah, so let's see. Right. Yeah. So if the table's full, then it'd be the same thing as array-based stack, array-based queue. We either say that the structure's full and we can't accept new data, or we need to go through a resize. Resize will be a little bit of an expensive operation. We'll see some of that later. I'm not sure we'll get that tonight or not, but we will take a look at that. Now, we will do other collision resolutions as well. Our next operation is going to be delete. Deleting a key from the table. All right, same basic operations. Cache the key, get an index, and then find the value. Once it is found, we'll remove it from the table. We'll need to keep in mind various collision chains that may exist when deleting the value. All right, so let's say we want to do a delete. Say we have our table here. Right. Table, these rows. All right, so let's go ahead and delete 5. All right, so we created a hole at index 4. So right now, attempting to look up 5 should yield a not found. Right? 5 hashes to index 4. 4 is empty. Return not found. Look up 16. Goes to index 4. 4 is empty. Turns not found. Right? So we have a problem here. So the easy solution is use a dirty bit to mark the cell as being previously occupied. All right, so they're going to be a literal bit value as a part of the object definition that is the element type or a sentinel value indicating the same. All right, so when doing the lookup, even though index 4 is empty, we'll treat it as occupied and walk over to 5 and find what we're looking for. On the next insert into the table, we'll treat indices that are empty and those with the bit set also as empty. Now 16, try to go to index 4, right? Because it has the same mid value as 5 did. So they're both trying to go to 4. Right? So the other thing Alternatively, we can collapse collision chains by taking a value from the end of the chain and dropping it up front. All right, so in this scenario, we can delete 5 and collapse. It's pretty easy to do. We just move the 16 over. We no longer have any collisions in this table at all. Look at when 16 goes to 4, and we find it at 4. Same thing with 10 and 12. They're all at the intended index. Right, this can be complicated if I have multiple chains here. So let's do this again. There's my table of data. And we're going to go with a simpler.
Professor, I had a quick question.
Mhm.
So you said that you moved 16 over in place of 5?
Yes, well, 5 was deleted. And then 16, since 16 also had same hash value, or the normalized hash value as 5 did, 16 took over its position.
So then that overwrites the dirty bit?
Yeah, so there would be no dirty bit. So this one would be in place of a dirty bit, we would do collapsing. So it's one way or the other.
Okay, thank you.
All right, so let's change my data here. So go 5. 5 goes to 5. 10 goes to 3. 12 goes to 5. 17 goes to 3. And we'll get here. 19. One more for good measure. Goes to 3. All right. 5 gets added to our table. 10 gets added to our table, index 3. No collisions just yet, but that will quickly change. 12 comes along, tries to go to index 5, but we have a collision, so it goes over the next available spot. And who's up next? 17 collides at index 3, goes over the next available spot. 19 comes along, goes index 5, wraps around to the front. Gets over collisions. And then 24. All right, goes index 3. Probe, 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 and finally found we're going to drop a value. All right, so let's say delete 5 again. All right, so our collision chains, which are crossing each other, we have 5, 12, and 19, right? All to be in the same index. And we have 10, 17, 24. All want to be at index 5 and index 3. All right, so deleting Before we get to delete, let's go verify. We can still find things. All right, so when we do a lookup for 5 and 10, right, there's no collisions, so they go straight to the corresponding index, no problem. Look up 12. 12 says go to 5. And you're not 12. So I'll go over 1, find 12, find what we're looking for, and we're done. 17, go next 3, not 17. Probe, find 17, and we're done. 19, let's go to 5, not 19, not 19. Wrap around, find who we're looking for. 24, long road to go. Starts at 3, not 24, not 24, not 24, still not 24, and we finally found 24. Some other value, 99. 99 goes to what, index 1, thereabouts. Not 99, empty spot, stop looking. Or if we're allowing for full table, we got back to where we started. Right, so say we're going for, 31. 31 goes index 3. Not 31, not 31, not 31. Nobody is 31, and we get to index 2. Index 2 is empty, and we'll stop looking for our data. All right, so the end. So we're deleting 5. So we're deleting from this particular collision chain. The last value in the chain, there's 19. All right, so we can take 19 out of index 0, drop it here, index 5. Now we do the lookup on 5. 5 comes to 5, not 5, not 5. It's 0, 5 is not found. Go to 19, right? 19 index 5 found, done. But we have a problem here with 24. 24 goes index 3, right? So not 24, not 24, not 24, not 24, hit an empty spot. Can't find 24, right? So we have, because of the the chains overlapping here, we have to make sure that we find that chain and collapse that one as well, so that we don't have an empty position when we're doing our lookups. All right, so it can get a little bit complicated trying to unwind chains, especially as the chains cross over each other, which is a table that's in a quite poor state to be in. One we'd like to avoid as much as possible, but the data is going to be what the data is, and the table is going to drop things where it's going to drop them. So dirty bit, even though it might be the lazy approach, not necessarily a bad approach, but it's certainly not great. If the table has a bunch of adds and deletes going on, the cost of unwinding the chains might exceed the cost of just setting the flag and adding the logic for the flag. But if the table doesn't change state often, collapsing the chain will be better. And generally speaking, when we're talking about hashing, the operation that we want to look up, optimize, is lookup. Most important operation with hash tables is the lookup operation. We expect to have orders of magnitude, more lookups than adds and deletes. Right, so going back to our website, go into the site, you log in, and then you do stuff in the site. So logging in triggers an add. Eventually, you'll either time out your session or you'll explicitly click the logout button. And that would trigger a delete from the table, because if you're not using the site actively, the server doesn't care about you at that point in time. So it's going to clean you out of memory so that other operations will work a little bit faster, because the smaller set of data you have to work with, the faster things are going to be in general. But in between those two windows of time, you're expected to probably do more than one operation, right? Tens of operations, navigating around the website, clicking on things, interacting with buttons, all kinds of stuff That's going to trigger activity against the server. And we'll need to look up data with your session to figure out what we're going to do uh, or what you're allowed to do, and add money, subtract money, make a post, whatever it is the website's doing. All right. Let's see. Got 5 minutes of break. Doing some math in my head. All right, let's go ahead and take a 5-minute break, and then we'll go over the test. And so that'll be the end of lecture for tonight. Go over the test. We'll cross-check. Where are we? Where are we with our labs? Hash table. Yeah, we'll talk about that first, then we'll talk about the test. All right, let's take 5. All right, hash table lab. Isn't really much code-wise with a hash table. Create an array, create a hash function, and it takes an int. And that function, all of one liner, returns a modulo of that int by the table size. Add function also takes an int. And then we'll go ahead and call our hash function from above, get our hash value. And then we'll try to add it to the table. If that position in the table is empty, just drop it in. And if it's not, use a linear probe for collision resolution. Curve the table. So yeah, you definitely, I'll show you, we have code. And close the file. So now I navigate away. And code sample for you to take a look at here. Lookup function, same idea. Takes the integer, hash that value. Then you look at that index, see if it's matching, and if it's not, start probing from the index through the table. And then if you hit an empty spot or the beginning of the table, you would just turn -1 saying I can't find it. All right, and a main function allows them to do all good stuff. All right, in the hashing folder, we got hashing.cpp. All right, we got a hash table class. It's got an array. It's got a probe function. All right, it's just a loop. All right, the only key thing you remember about this is to make sure we are circular, right? So we need a modulo by the table size. So we stay within the bounds. And not much to it. All right, here's again means modulo size. Make sure we stay inside the bounds. So we're going to make a circle around the array. So if we hit the end of the array, circle back around to the front. And right, we do have this looping test stops us from getting to a forever loop because the table is full. Right, it's possible for the table to be full. We'll look at .NET implementations next week, and we'll see how it's doing its resizing. And we'll talk about resizing because it involves basically creating an entirely new, remaking the table from scratch because the table size, if it gets bigger, table size, regardless of what hash function we're actually using, we have to normalize it to a good index in the table because, you got to stay within bounds of the array. And the table size is a part of that calculation. Okay, test 3. Forget for any other questions about the lab. All right. Trees. Oh, forgot to grab the code. Okay. One moment. One of the things I don't like about Canvas, like layers and layers and layers and layers to get to a particular field. Their tree hierarchy is way too much. Right. Almost there. Big O notation, right? So turn the smallest value from the heap. Right? We're not deleting, so we're just looking at the smallest value. It's min heap, so the smallest value will be at the root. What is the big O notation for the following operation? Adding to a binary search tree. So binary search tree is not necessarily balanced, so we're going to be linear time. 2-3 tree is balanced, so it'll give us logarithmic time. Expression on an expression tree, right? That's the linear time because it's traversal. We have to hit every vertex in the tree. Smallest value, so returning the smallest value from a max heap, right? So that's gonna be a traversal. Look at every vertex in the tree because it could be any of the leaf values. Add a new value to a min heap. All right, min heap's balanced, so log time. Value 2-3 tree is balanced. AVL tree balanced. Searching a max heap, right? It's gonna be linear. Searching is not a well-supported operation for a max heap if supported at all. Weird white space. Okay, actual height of the tree. Right, so length of the longest path from root to leaf, lowest leaf, can be used to determine the height. 7, 8, wherever it is. The airiness isn't going to help us. Trees definitely have height. Number of levels in the tree would tell us the height of the tree. Number of nodes in the tree is not enough information. If it's a specific type of tree, then we could do that, but this doesn't call out a specific type of tree. And being balanced or not is not necessarily going to tell us how tall the tree is, right? I can give you two balanced trees that are different heights. And right, so it's not enough information. Yeah, so determining a tree height. So if I say like an AVL tree or a B tree, specifically a 2-3 tree, then the number of nodes could tell us the height of the tree because there are going to be defined ranges. AVL, not so much. A heap and a 2-3 tree. Number of nodes in the tree. Yeah, not so much. A heap, we could do it from the nodes. 2-3 trees got too much variability. You'll have overlap in bigger trees just based on the node count. Which trees are array based? So our heaps are array based. Build a tree. Okay. So we've got 27 and 49 to start. 19 comes along. 24 gets added. 39 gets added. And we got 71. Causes 49 to promote. And their existing 19 node. 88 gets added. And then 20 causes 19 to promote. Which causes 27 to move up, which makes 27 the root. Any question? I'll leave that up there for a moment. I'll build this next tree. AVL tree 35, 49, 22, 27. No imbalance just yet. 64, and then now 60. Because a double rotation. So 60 will move up. 49 goes down. 64 will carry up with it. And then the rest of our tree would be as the same. So I didn't even use the rotation, just want to know who alpha was. So 49. All right. Any questions about number 12 or 13? Okay. Wipe that away. Move along. 14. Binary search tree. Who is on the third level? All right. So it's definitely not 48 because that's the root. Not 37 or 69 because those are on the second level. All right. So we got 55. 5's on the third level. 19 is on the third level. 31 is not on the third level. 42. 42 is on the third level. 88 is on the third level. My third level's full, so I don't even need a botter. 53. And our max heap. 17, 12, 24 will supplant 17. And 28 will supplant 24. 23 adds, no change, 21. And then 5. All right. Second level, 24, 21. Questions about either of these two questions? Questions about a question. That makes lots of sense, right? All right, I'll knock that away. 16 in order traversal. All right. I just like doing the math. Probably easier to draw this out. Okay, so we got 44 at the root. 31, 69. Empty left subtree. 41, empty left subtree. 75. All right, so inner traversal. 31, 41, 44, 69, and 75. And the root. And we're doing one base, right? First, second, third. All right, so third position. Post order traversal. All right, so we have D, B, F, G, C, A. All right, we go to first leaf, knock it out. Next leaf, knock it out. Use the leaf, knock it out. Work our way over to another leaf. Two leaves. This is now a leaf and makes the root a leaf. And it's the last out. So we've got Deb, FGCA. Questions on the post order? Build a max heap. Well, it's a max heap, so 23 is in the root. Array-based tree, what could that tree represent? All right, so draw our tree. All right, so assuming it's a binary tree, since that's our default arrangement for trees. Okay, where we are. 7, null, 38, and then 58. All right, so we have a binary search tree. Could be a binary tree. It would be height balanced because of this empty position right here. It's not going to be any of the heaps. 2, 3 trees are not array based. All right, so we'll go with those 3. All right, trying to make this a heap, it wouldn't work. Try to make this a min heap. 2 children be like, nope, 14 can't be below 25 as a min heap. Go max heap. All right, and then 49 says, nope, I can't be below 25. So eliminates heaps for those reasons as well. Perform a delete. All right, so 4 is going away. So it's not that answer. It's not that answer. It's not an answer leaving a hole at the root. Not that answer. Not that answer. So the question is it none of these or this one? So let's see. We've got the hole at the root to populate. 9, 6, 7, 8. All right, so 8's falling off. 5 promotes up. 6 takes its place, and then 8's here, so that gives us 5, 6, 7, 9, 8, 7. So 5, 6, 7, 9, 8, 7. AVL tree. If it's a small enough tree, that's true, but it is a binary search tree. It's a binary tree, and it is balanced, but it's height balanced, not weight balanced, so that does not apply. All right, 22. Post-order traversal. All right, so we have traverse. Traverse version. If the root. Traverse the root. All right, otherwise. A message. Whatever it is, don't much care. Then we have binary node star subtree. If sub, or if not sub, yeah, tab key doesn't work. So funny. You just bail out. Otherwise, traverse, sub left. Oh, that was nice. Kill my white space I so worked hard on. Traverse right. See out, root. What I call the data value. Oh, white space or whatever, it doesn't much matter. Okay, postword traversal. And leftmost leaf. All right, so this one, to get the full answer is a little bit tricky. You didn't get the full answer, that's okay. That just means you got extra credit. All right, so memory leaf is a node with no children. All right, so find leftmost leaf. If root will return my leftmost leaf on the root, otherwise return -1, indicating we have an empty tree. And binary node star root. Okay, so if we have a node here, and we can start testing, see if this is a leaf. All right, so if root left is equal root right, which means they're both null, we can return, what do we call this one? Same thing, value. All right, so we can start our first test case. Null tree, we get back -1. Okay, tree with one node that has 4 in it, or whatever the value is. Root exists, call the function, come in here, root exists, root left is null, root right is null, 0 is equal to 0, return back 4, and we're done. All right, so let's make this tree. Not that scenario, so we have a left node. So we're going to go left. All right, so if you have to be careful here, white space. So there's my eraser, eraser. All right, so binary node star temp equals root. While temp equals temp left. All right, so in this case here, right, come in here, root left is not null, so 0 is not null is not equal to null. So we'll come left. So at this point we have temp here at root. Right, so if we were just stop here, and I should say while temp left. While temp left. So at this point, tab. Temp is at 2, and it would return 2. So it works just fine for that. But what if we add, say, 3 here? And the code falls down. Right, we come in, root has the left, so that's not true. It's at temp moves over, temp stops when it gets to 2 because there's no left to go to, and it tries to return 2, but 2 is not a leaf, so we need to account for that. So what we would do here, if temp right, go ahead and make a recursive call, find leftmost leaf, temp right. All right, so come back in here again. We start at the root. Root, left, and right are not equal to each other. Temp is the root. All temp left, right, the loop doesn't loop very far. There is a right, so we'll go ahead and call the same function with right. So we're over here again. Find leftmost leaf with a node. That node has no left, it has no right, so return back 3. And then it comes up and then turns back 3 from here, and we're done. If there was more down here, right, that would not be true. We'd go to our temp, we'd slide down. So we'll do a lightning bolt down however far we need to go until we get to an actual leaf node somewhere down in the tree, favoring the left direction. It doesn't necessarily have to be a binary search tree, right? It's just a binary tree. And it could be a binary search tree. That wouldn't matter. Uh, Finding the leftmost leaf. All right, let's see what I broke on the key. Breaking happens. All right, nothing's broken at the moment. I think I saw someone got 80%. I was looking at it earlier. All right, grading to be done. It's possible you get over 100% on this test because it's very common to solve this problem by doing, right, just, kind of like the homework, just keep going left until you get to the leftmost node. And then presuming that's a leaf, but that's just the leftmost node, not the leftmost leaf. So it's close to the solution, but not quite the solution. Any questions on the test? Any question numbers we need to go look back at again? Yep. A right child could very well be the leftmost leaf. In fact, go into this scenario. All right, 2, 1, whatever this binary tree is. All right. When you're building an algorithm, start with the smallest, like if it's a tree algorithm, right? Start with the smallest trees you can come up with. All right, so we got an empty tree, a one node tree. We've got our two node trees. And then from there, then you can start, right, making ugly trees. There's no points off if you didn't account for the rightness. You simply get extra credit having accounted for rightness because the right node could well be a leaf. Right, so long as you have logic, if you have logic in there that actually checks for a leaf at some point, that's good. And you have a general traversing left pattern, then we're good. As long as we're avoiding any null reference errors, should be good for full credit. And if you also accounted for the fact that leftmost leaf might go down one or more right paths, right? Because we'd have a tree that looks like this, right? There is one leaf in this tree. And getting there involved going to the right a couple of times. Right? So that's one of the things that can be very hard to learn is try to think what scenarios are these and what are the bad scenarios? What scenarios are going to try to break my code? Because happy path. That's the easy road. That's the one that gets heavily tested and everything's all happy go lucky. But the unhappy path, that will happen. Right? See if can I draw a devil? No, not so much. There you go. That's a devil. Unhappy path happens all the time, and we'll try to break your code. So you gotta try to account for those things happening. Uh, yeah. Leftmost node is just the leftmost node. If it's binary search tree, then it's the node that's the smallest value, but otherwise, not necessarily leftmost leaf. All right, now's a good time to jump jump on that hash table lab. It's due in several days. If you have questions, I'll keep hanging around, but otherwise, I don't have anything else to pass your way for tonight. Have a good night, and we'll talk to you later.